Okay, so because record just started, let me just, so here we just repeating the previous, the end of the previous lecture where we introduced Jacobi method. So this is the matrix form of Jacobi method. So now, okay, so if we substitute U0 into the equation for V1, so we will get the following. Okay, now, the only problem which I see here is the following. So we use in this equation U0, right, in order to get V1. But the problem is that we are applying this algorithm line by line, right? So if we first calculate this, and then here, I mean, if I have convergent algorithm, then U1 will be already better approximation than my initial guess, right? So at least I hope so. So idea of Gauss-Seidel method is the following. In Jacobi method, let us use here already not the old approximation, but everything which we obtained before. So here we obtained U1. So as a result, instead of using U0 here, let us use U1, just like that. So it would change our approximation, just our method, iterations method, just a little bit. So you see, we here use already hopefully better approximation, UN plus 1. So how to formulate it in the matrix form? So essentially, we use the same formula as before, L plus D plus U for the matrix A equals to the right-hand side. And now I will leave L plus D here, and here will be B minus UX. Okay. Now, what will be the what form will have this matrix? So it's essentially lower triangular form, zeros everywhere here. Just like that, right? So now I can do the following. So it will be very easy to find the first component of X, right? So it will be just, if I will write it like that, n plus 1, n. So it will be very easy to find the first component of x n plus 1, right? Why? Because for the first component, I will get just x n plus 1, 1 equals to correspondingly the first component of b minus u x n, the previous approximation, first component, right? Then here, what I would have L, so this matrix would give me L 2, 1 on x n plus 1, 1 plus D diagonal element 2, 2 on x n plus 1, 2. and this will be equal to some right-hand side, right? Which includes only the previous iteration. Now here, I could already use, I can reformulate it in the following way. xn plus 1, 2 equals to this right-hand side. No, okay, let me write it in proper form. b minus u xn, second component. So I will just write it like that. b minus u xn second component minus L to 1 xn plus 1, 1 divided by d to 2, right? So essentially, you have system of linear equations with the lower triangular matrix, which you can use using forward substitution, right? So in this case, you are always using the results of all the previously computed components of xn plus 1. So like here we use previously computed updated component of xn plus 1, 1, right? To compute the second component of xn plus 1. So we are using the first component, which we just computed in this line, right? So essentially, you can formulate it in the following form. So I can write it like that. So if I look in here, so you can either apply forward substitution using the equation which you have already, or you can do the following: dxn plus 1 equals to b vector minus u xn minus L, so this on that, right? xn plus 1 vector. So pay attention, because we have a lower part, so it's exactly these components, all the previous components which we already computed here. So you can formulate it like that. So there is no contradiction, because essentially you can start from here, and you will see that you are just doing a forward substitution. So for every next component of your next iterate, right? So hopefully better approximation if you have conversions, right? So for every next component, you are using your previous components because you are performing forward substitution. Is it clear or not? Any questions here? So you see, the thing is that you will need to do these in your next homework. So I want you to have all the information to do this. So please ask me questions if you don't understand something. Okay. Yeah.
I was just wondering, so could you go over again what the subscript 1 and 2 mean for the right hand side? So like
yeah, sure. So you see, what is xn plus 1? It's x n plus 1, 1, right? X n plus 1, 2, and so on till x n plus 1 nth component, right? Or if you like, I can say kth component, right? So if you have k-dimensional vector. So if I have, so this is L plus D, lower entries and diagonal entries. So this will give me the lower triangular matrix, Is it clear or not?
Yeah, that's clear so far.
And now you see, if I will multiply the first row, right? So it contains just one diagonal element, right? So here, so it will be really, yeah, d11 xn plus 1 1 multiplied on that, right? Is it clear or not?
Oh, yeah.
And because what does it mean that vectors are equal to each other? It means that all corresponding components of the vectors are equal, right? So here we have d11 on xn plus 1 1. And here we have just the first component of the right-hand side, right? Is it clear or not?
Right, yeah.
Yeah, because this is just a vector, right? So which I can compute, right? Because I know my previous approximation xn, right? So from here, I immediately can find just dividing by d11. So dividing by d11 here, right? So I can write the first component of the new approximation. Is it clear or not?
Yeah, that makes, I think it's clear now. Thank you.
Yeah, and now if you consider the second line, right, it would include the lower because it's lower triangular matrix, right? So it would include these component and diagonal components, right? So this is the first component. So this one, right? And diagonal component, which is this one, right? Clear? And here we already can use this thing, right? So because we already found it. And then for the next component of the vector xn plus 1, you're using results of the previous computation, already updated components of the vector. And of course, as you can understand, so further here will be, in order to find the third component, we will use all previously found components. So this one and this one, right? And so on and so on. Is it clear or not how I'm doing this?
Yes, that's, it's clear now.
Mm-hmm. And condition for convergence is more or less the same. So it's you need to have diagonally dominant matrix. I mean, you can ease a little bit some of these conditions, but it's definitely outside of this course. So please take numerical linear algebra course if you're getting interested in this, because this is really extremely important. Why? Because in many cases, so one could say that what for on earth I would need to use these iterative methods when I have this wonderful LU factorization method, right? But the problem is that when you perform an LU factorization, you know that it's 2/3 n cube operations, right? Here, if you know how to multiply cheaply your matrix or parts of your matrix, like here and here, on the vector, and in many cases you can do this for sparse matrices. Like you remember, we considered 3 diagonal matrices, right? So you can do this cheaply. And so, for example, to multiply by the upper part of the 3 diagonal matrix is just n operations. To multiply by the lower part, it's again n operations, order of n operations. So this is just multiplication by the diagonal matrix, again order n operations. So as a result, to get every approximation, so you need just order n operations, not n cubed, but n. So it's way faster, right? So if n is, let's say 100, so then n cube is 1,000, right? I mean, 1 million, sorry. So while here you will still have, okay, maybe 300, maybe 500 iterations, doesn't matter. So it's way less. So not always you need just, you know, we know that anyway we will get, we have swamping, we have condition number of a matrix, and so on and so on. So even if you use LU factorization, you will not get exact solution, right? So in most of the cases, so because you have these round off errors, condition number, and other things which we already considered, right? So this is why in many cases iterative methods are preferable. And now so we formulated this Gauss-Seidel method. So this is yeah, here. So this is modification of Jacobi, which is called Gauss-Seidel method. Okay, now let us consider something a little bit better. I mean, as you will see, it's in some cases it's better, in some not. So it's called, so essentially idea is the following. Let us make a step in the direction of Gauss-Seidel method, but let us try to overshoot, to go a little bit further in the direction of for the next approximation, in the direction of this step, so that we probably will get a little bit faster to the solution. So you see here I'm using this probably, and so on and so on. So okay, idea is the following. Once again, let us essentially consider the following example. Let us consider the following equation, system of linear equations. Right? Example. So let us formulate Gauss-Seidel iterations. So first, okay, could you tell me what will be the lower part of the matrix? So here it is, the diagonal part. So what will be the lower part of the matrix? Could you tell me?
2, -1, 2.
Yeah, but how the matrix will look like? So it's essentially, I told you, so you fill everything with zeros, everything else, right? 2, -1, 2, and everything else is filled with zeros, right? What will be the diagonal part of the matrix? Could you tell me?
Just elements 3, 4, and 5 on the diagonal, and then zeros elsewhere.
Yep. Okay, what will be the upper part of a matrix?
All the arrow except 1, -1, 1.
Mm-hmm. So you can see that A can be obtained as L plus D plus U, right? Because you just add corresponding elements and you will get back your original matrix A, right? So, okay, so then Gauss-Seidel will look like that. So it's just have a look here, right? So we are having xn plus 1 equals to, what will be D inverse? Could you tell me? Just inverse, so the same diagonal matrix, just with the 1 over elements on the diagonal. So 1/3, 1/4, 1/5, right? And zeros here and here. Okay, multiply it on the right hand side, which is 4, 1, 1 minus upper part 0, 1, -1, 0, 0, 1, 0, 0, 0, multiplied on the previous, so this term, right? Minus 0, 0, 0, 2, 0, 0, -1, 2, 0, multiplied on xn plus 1. Or you can formulate it in this form, so like that. So you essentially write it 3, 4, 5, 2, -1, 2, 0, 0, 0, xn plus 1 equals to 4, 1, 1 b, right? And this is nothing else but L plus D minus 0, 1, -1, 0, 0, 1, 0, 0, 0, xn. This is U, right? And this is, so xn, you know, right? So you can multiply it. And then you're getting system with lower triangular matrix, right? For some right hand side. So as a result, you can solve it using forward substitution. So, okay, let me write it in components. So you remember in X we have a first component U, second V, third W. So you have U, let's say K plus 1 equals to 4 minus, we use N, so let us keep it like that. 4 minus, so this 4 minus V N, right? So remember that this is UN VN WN, right? So we're multiplying and getting VN plus WN divided by the diagonal 3, right? So then VN plus 1. So we have 1 minus 2 UN plus 1. So we use already information here. Minus VN divided by 4. WN plus 1 equals to 1 plus UN plus 1 minus 2 VN plus 1 divided by 5. So essentially what I have done, I just have written these in the components with the corresponding inverse diagonal matrix. So you can see that it's exactly 1/3, 1/4, 1/5. So 1/3, 1/4, 1/5, right? And so on and so on. So this is Gauss-Seidel. Okay, now let us do exactly what I said. So we will use the weighted average average of not W but omega. Omega times Gauss-Seidel and 1 minus omega times current guess or current approximation. So how it will look like? I will use, okay, so un plus 1, vn plus 1, wn plus 1. So 1 minus omega times current approximation. So 1 minus omega times un, 1 minus omega times vn, 1 minus omega times wn, plus omega times Gauss-Seidel. So this 4 minus vn plus wn divided by 3 plus omega 1 minus 2 un plus 1 minus wn divided by 4, and here omega times Gauss-Seidel 1 plus un plus 1 minus 2 vn plus 1 divided by 5. So essentially, I just used this, and that omega times. So you see with factor omega. Now, of course, the question is how to choose this omega. Okay, so I will show you the example for some serious matrix, relatively big one, and you will see that essentially the choice of omega. So you usually use it. You take it omega. So if you have it strictly more than 1, so you have overshoot, right? So you go a little bit further in the direction of the Gauss-Seidel, right? And you, for example, if you take omega not far from 1, so if, for example, you take omega equal to 1.1, so you go in a little bit further in the direction of Gauss-Seidel and subtracting just 1/10 of the previous approximation, right? So as a result, as you will see, so in some cases, choosing the right value of omega, we can get a little bit faster convergence. Okay, let me show it. So okay, so here it is. So this is our Gauss-Seidel iterations, which we just have done, right? So now we are doing so-called over relaxation, or overshooting in the right direction. And so as you will see that convergence is a little bit faster if you choose omega right. So, okay, let us consider more or less realistic example. So we have a sparse matrix, you see? So we have a lot of zeros, right? Everywhere in the matrix. And we have a strong diagonal part. So this looks very much like a solution of the of some ODE with the second derivative in it. So second order ODE. So then, if you are solving problem like that, so pay attention that, for example, the upper part contains almost only this diagonal thing and just few elements, few other elements. The lower part contains almost only this sub-diagonal thing, right? And few other elements. And diagonal is just simple, it's just equal to 3. So essentially, if you apply, let us consider what will happen if we apply different methods. If we apply Jacobi method, so you see, so yeah, solution is 1, 1, 1, 1, 1. So if you apply Jacobi method, so this is the 6th component. So this component of a vector. So you see, we are getting closer and closer and closer and closer, right? So approaching, we have convergence, we approach, and yeah, by the way, could you tell me, is this matrix diagonally dominant or not? So for example, here in this row, what is the diagonal element? 3, right? How to check it if it's diagonally dominant? Absolute value of this diagonal element has to be strictly diagonally dominant. It has to be strictly more than sum of absolute values of all other elements. So have a look. 1, absolute value is 1, plus 1, 2, plus 1/2, right? So 2.5. 3 is strictly more than 2.5. That's it. So essentially, you can see that here you will have the same, and all other elements, they contain their diagonal dominance will be satisfied even better. So it's convergent, right? So you see, we have, this is Jacobi method. You see Gauss-Seidel, which uses information, right? So have a look. Even on the first step, Gauss-Seidel gives you a better approximation of 1, right? So less error than the Jacobi method on the 1, 2, 3, 4, 5, 6 step, right? So even on the first step, Gauss-Seidel gives you better result. So because it uses already information about the previous steps. So updated information, I mean. So you see, it's getting closer and closer. But what will happen if with this overshooting method, so-called successive over relaxation, so when you overshoot a little bit in the direction of Gauss-Seidel method, so you're getting even faster convergence. So here we have chosen omega to be 1.1. So now we can really investigate the problem. This is another example. Yeah, this is another example. So, but idea is the following. So you see, this is dependence of L infinity error, which means that the maximum error, the maximum error component, magnitude of the error component, right? So if you just subtract our xn plus 1, subtract from the exact solution, and just draw the maximum component of the result. So this is what happens. So you see, error is decreasing with omega when we go a little bit further than 1, right? But then if you overshoot too much, it starts to increase. So, and for this particular case, so you see we have chosen it almost ideally, because the minimum is approximately omega equal to 1.13. So it's very close here. So we are sitting here, but this is the minimum is a little bit further here. So, okay, let me stop sharing. So this is called successive over relaxation, or SOR method. So it's essentially, in a way, you can say that this is generalization of Gauss-Seidel method, because if you choose omega equal to 1, these terms will turn to 0. So you will get just when omega is equal to 1, successive over relaxation will turn into Gauss-Seidel method, right? Nothing else. So you are trying just to go a little bit further toward the solution. Okay. Any questions here? Okay. So what I wanted to tell you, so you remember on the last lecture we considered the case when we just exchanged these equations and tried to apply the Jacobi method, right? So, and it was divergent. So you see, you can play a little bit with your metrics to get strict diagonal dominance. For example, you can multiply it by some numbers, some rows, and so on. So you can try to get your matrix to the strictly diagonally dominant form. So, okay, I will stop here. So now you have everything to do the first part of your homework. So, and I will come back to the interpolation. So let us remember, so what we had. So let us consider data points, 4 data points, right? I goes from 1 to 4. So we have 4 pairs of x and y's, right? So correspondingly, if we have 4 points, we can use 4 basis vectors, right? So let us use the basis of monomials. Which means that we are using 1x, x squared, x cubed, right? 4 vectors. So, and it will allow us to use the following Vandermonde matrix: 1, 1, 1, 1, x1, x2, x3, x4. So remember, it's just values. So every column is a value in every point of the corresponding basis function. So x1 squared, x2 squared, x3 squared, x4 squared, and x1 cubed, x2 cubed, x3 cubed, x4 cubed. So this is Vandermonde matrix, right? So, and we essentially solving the problem like, let's say, VC equals to Y. So where Y are corresponding Y1, Y2, Y3, Y4, right? And our interpolant supposed to satisfy C1. So component, first component of vector C, C1 multiplied on X plus C2 multiplied on X, and here is C3 X squared, C4 X cubed, just this. Okay, so first of all, here we have a dense matrix, right? So LU factorization, so solution of this system of linear equations would require 2/3 and cube operations, right? So if number of points, usually number of points is way more than 4, right? So 2/3 and cube operations, where n is the number of points. Okay, so there are also good things about this method, but we will discuss them later. So, okay, now, can we use different bases, not bases of monomials, which is very simple, very natural. So it's even in the vector space of polynomials, this is called so-called natural basis, right? So let us use a little bit different basis. Okay, let me do this. So let me consider P4 hat, which will look like that. 1, x minus x1, x minus x1, x minus x2, x minus x1, x minus x2, x minus x3, basis like that. So you see, it's once again 4 vectors, 1, 2, 3, 4. By vector here, I mean element of a vector space, or you can say that these are 4 basis functions, right? Okay, so you can show that these basis functions are linearly independent, but the main thing is the following. If you have distant points, main thing is the following, that pay attention, this is what we had. We had, so what is Vandermonde matrix? It's phi1 x1, phi1 x2, phi1 x3, phi1 x4, right? Phi2 x1, phi2 x2, phi2 x3, phi2 x4, and so on, right? For phi3 and phi4. So this is our phi1, this is our phi2, phi3, phi4, corresponding basis functions. Now, have a look. I will get the following matrix: 1, right? Okay, so 1, 1, 1, 1. It's easy. Now have a look. When I substitute phi2 here, so, and here I have phi3 x1, right? Phi4 x1. Because I have difference of x and x1, so if I substitute here x1, so what I will get in the remaining entries of a matrix? in the first row here?
You'll just get zeros for the remaining entries.
Yep, exactly. Okay, let me just write it here so I will have more space. So I will have 0 here, right? And let's say 0 here and 0 here. Okay, below what I will get? So just tell me, I'm substituting into phi 2.
X2 minus X1.
Mm-hmm. Below?
0, 0.
No. So you see, I'm substituting x2. Now I need to substitute x3 below, for the element below.
X3 minus X1. X4 minus X1.
Okay, great. Thank you. Now, when I'm using f3, so because it contains x minus x2, right? I know that I will get 0 here, right? In all components here, which, I mean, I will get 0 here, okay? So below I will get x3 minus x1, x3 minus x2, right? And here x4 minus x1, x4 minus x2, right? Is it clear or not?
Yes.
Okay, so now this component phi 4, it contains x brackets with the difference of x and x1, x2, and x3. So it means that first 3 elements will be zeros, right? And the last element will be x4 minus x1, x4 minus x2, x4 minus x3. Okay, what can you tell me about this matrix? It has a special form, right?
It is a lower.
Lower triangular, right? So it means that when I will be solving this system of linear equations, what can I use? So how we solve system of linear equations with lower triangular matrices? Using what approach? Okay, tell me, please. We just did it here, for example. Forward substitution, right? Because the first equation is easy to solve. You just need to divide by the diagonal element, the right-hand side by the diagonal element. Next equation is also easy to solve because you can use the previous information, and so on and so on. So forward substitution. Could you tell me what is the complexity of forward substitution? We estimated that. So it's scales as so if LU factorization scales as n cube, how the forward substitution scales, the number of operations for the forward substitution?
Does it just scale with n?
Forward substitution, it's a little bit not so easy. For tridiagonal matrix, it scales as n, but for forward substitution, it scales as n squared. So we counted these operations, and you can easily get it. So it's good exercise, by the way, to show that it's n squared. So essentially, yeah, just like that. So this is called, so this basis is called Newton's basis. So this is basis of monomials. So polynomials which contain only one term in corresponding power, right? So this is x to the 0th power here. This is x to the 1st power, right? Second, third. So here we use a little bit different bases. So you see, instead of linear term, we use this one. Instead of quadratic term, we use this one. Instead of cubic term, we use this one. So powers are the same, but it contains a little bit different expressions. So it's not basis of monomials anymore, but what is interesting that the matrix, the Vandermonde matrix, will look like that. So it's lower triangular, so that we can use forward substitution and easily solve the problem. But so this is Newton's basis leads to lower triangular Vandermonde matrix. Okay, so I will show you the way how to compute the coefficients even without solving this lower triangular matrix. So there is a way how to compute those coefficients for the corresponding. Yeah, let me just write it. So you will get the following approximation of your function. So it will be C1 multiplied. So this is phi1, right? Phi2, phi3, phi4, right? So you will get C1 multiplied by 1 plus C2 multiplied by x minus x1 plus C3 multiplied by x minus x1, x minus x2 plus C4 multiplied by x minus x1, x minus x2, x minus x3, right? So these C's are from here. So components of the vector C, so from the system of linear equations with Vandermonde matrix, right? As we considered before. So now there is a way how to find these coefficients using very simple algorithm. So let me give a definition, and then I will use it. So it's a definition of Newton's divided differences. So essentially, these Newton's divided differences you can get if you just apply Gaussian elimination. For this matrix, and you are getting Newton's divided differences. I will not prove it, so there is a proof in the book, so if you like, you can go through that. I just want to give you an algorithm how to find. But you can find it easily by yourself. So just using the Gaussian elimination for this Vandermonde matrix. Let f of x be a function and x1, x2, xn a collection of distinct data nodes. Distinct means that none of these x's are equal to each other, right? So it's important, as you will see. Define the zeroth order divided differences as f xi will be equal to just the value of our function in the point xi for I going through all the points. Then for all I, which is equal to 1, 2, and so on till n minus k, the kth order divided differences are given by f xi xi plus 1 so until xi plus k is given by the previous order divided difference Pay attention. So here we start from xi, here we start from xi plus 1. So if this is kth order, this is k minus 1th order. So here the number of points is k plus 1, which is used, right? So you see, for zeroth order, we use 1 point, right? For kth order, we use k plus 1 points. Okay, so this is k minus 1th order minus xi plus 1 xi plus k minus 1. So this is also k minus 1th order divided by xi plus k minus xi. So let us do an example, and it will help us to see through the definitions. So, example. So let us consider D5, 5 points data set, which is 1, 1, 2, negative 2, 3, 4, 4, negative 1, and 5, 0. So usually you compute these divided differences using a table. So x1, x2, x3, x4, x5. So 4 points, 5 points, sorry. So zeroth order divided difference is nothing else but, so this is zeroth order divided difference, which is nothing else but the value of our function, right? Then, so it's zeroth order. The first order will include 2 previous. So pay attention that kth order uses difference divided by the difference of x's for k minus 1th order. So this is f x1, x2, f x2, x3. So first order divided differences. So this is 0th order. So here is x3, x4, and here is x4, x5. Okay, so then we go further. So this is first order. Then we go further, so we get together these. So here we are getting this, here this, here this, here this. So here we are getting this, so it will be x1, x2, x3. Here will be f of x2, x3, x4. Pay attention, so here we're using x2, x3, here x3, x4. So here we are using 3 points already. And here, because have a look, the formula uses here, it uses k points, right? I plus 1, I plus 2, I plus k. So it uses k points. Here it uses k plus 1 points. So here it will be x3, x4, x5. Have a look. x3, x4, x4, x5, right? So altogether x3, x4, x5. So here it's f, x1, x2, x3, x4. So this is second order. F, x2, x3, x4, x5. And the last one, I will write it here, f of x1, x2, x3, x4, x5, all of them. So this is third order. And this is fourth order. So we cannot go further because we don't have enough points, and you see the points are decreasing. The number of elements is decreasing with the order, right? So if we had 5 points, so 5 minus 4 will give me just one coefficient, this one. And I cannot go further. So, okay, we will compute these coefficients on the next lecture.